Today, we will talk about an organ that rules all of our body, and that is our brain. As it is the most sensitive organ, our brain is kept inside a bony covering called skull. From doing physical activity to solving logical problems, from dealing with emotions and feeling to creativity, the brain is responsible for all. Therefore, it never sleeps. Our brain can be divided into three main parts: the cerebrum, the cerebellum, and brainstem. Cerebrum is the largest part of brain, which can be further divided into right and left halves, called hemisphere. Each cerebral hemisphere has four lobes, namely frontal lobe, parietal lobe, occipital lobe, and temporal lobe. Each lobe performs different functions. Cerebellum is responsible for movement and coordination. It gives you sense of balance and thus prevents you from falling down. Brainstem includes midbrain, pons, and medulla oblongata. It controls your body's involuntary actions, like breathing, heart rate, and blood pressure. Brain comes under a system called nervous system. Structurally, nervous system is classified into two types: central nervous system, CNS, and peripheral nervous system, PNS. The central nervous system comprises of the brain and spinal cord. The spinal cord is the bridge that connects the brain to peripheral nervous system. It starts from medulla oblongata and stretches to lumbar region of the spine or vertebral column. The peripheral nervous system is a network of nerves spread across our body. Think of peripheral nervous system as a network of highway that connects the body with central nervous system. This highway has two-way traffic. Let's see how. When you hold a hot cup of coffee, sensory neurons in your hand transmit signal to brain through sensory neurons, also called afferent neurons, that the cup is hot. Your brain processes that information and send response through motor neurons, known as efferent neurons, that you must put that cup back. PNS consists of total 43 pairs of nerve, among which 12 originate in brain, named as cranial nerves, and 31 originate from spinal cord, hence called as spinal nerves. Here you hear the word neuron. Neuron is the basic unit of nervous system. It is the nerve cell which transmit electrical signals to brain. A neuron has three parts: dendrites, soma or cell body, and axon. Dendrites serve as input device for neuron because it receives input from other nerve cells. Soma or cell body of neuron contains nucleus. Axons serve as output device from where it transmits electrical response to other neurons. I hope this helps you in understanding nervous system.
When the cell membrane is at its resting membrane potential, the activation gates of the voltage-gated sodium ion channels are closed and the inactivation gates are open. Voltage-gated potassium ion channels are closed. Depolarization is initiated by a stimulus which makes the membrane potential more positive, causing the voltage-gated sodium ion channels to start to open. As threshold is reached, many sodium channels open. Sodium ions diffuse across the membrane, causing depolarization. Voltage-gated potassium ion channels also begin to open, but more slowly. Therefore, depolarization occurs because more sodium ions diffuse into the cell than potassium ions diffuse out of it. As the membrane potential approaches maximum depolarization, the inactivation gates of the voltage-gated sodium ion channels begin to close, and the diffusion of sodium ions decreases. The potassium ion channels remain open, and potassium ions continue to diffuse out of the cell. The increased potassium ion permeability lasts slightly longer than the time required to bring the membrane potential back to its resting level. The extra efflux of potassium ions causes the membrane potential to become slightly more negative than the resting value. After the voltage-gated potassium ion channels close, The active transport of sodium and potassium ions reestablishes the resting membrane potential.
In this video, I'm going to explain an action potential. An action potential, or a nerve impulse, causes a movement of ions across the cell membrane of a neuron, similar to a ripple passing along the surface of a pond. The cell membrane of a neuron contains thousands of tiny molecules known as channels. These channels allow either sodium or potassium ions to pass through. Generally, the channels on a neuron are closed, and the membrane is said to be in a resting state. In this state, the charge of the inside of the cell membrane is more negative than the outside. And if you could imagine sticking microelectrode connected to a voltmeter inside this membrane, the reading would show about negative 70 millivolt, meaning that the inside of the neuron is about 70 millivolt less than the outside. The cell membrane of a neuron is polarized because of this electrical difference across the membrane. Now, a nerve impulse starts when pressure or other sensory inputs disturbs a neuron's plasma membrane to the point that the potential difference reaches a threshold voltage of about negative 55 millivolt. This causes hundreds of sodium channels in that region of the membrane to open briefly. This in turn allows positively charged sodium ions to flow inside the cell membrane. Now the inside of the membrane temporarily becomes more positive than the outside, which in turn causes the voltage to rise. This is called depolarized state. The membrane is now depolarized because the net charge inside the axon changed from negative to positive as sodium ions entered in. As the impulse passes, the potassium channels begin to open, allowing positively charged potassium ions to flow out, which causes inside of the axon to resume a net negative charge. At this point, the voltage would fall. The membrane is now said to be repolarized because again, it's negatively charged on the inside and positively charged on the outside. Now, this depolarization and repolarization of a neuron membrane is called an action potential. Action potential is just another name for a nerve impulse. After a nerve impulse, some voltage-gated potassium channels remain open, resulting in further movement of potassium out of the cell. As the voltage falls below the reading of the resting state, the membrane is said to be hyperpolarized because it's even more negative than at the beginning. At this stage, neuron is unable to conduct a nerve impulse and it's said to be in the refractory period. The refractory period is a very short period during which the sodium-potassium pump continues to return sodium ions to the outside and potassium ions to the inside of the axon, thus returning the neuron to resting potential. So in summary, an action potential is just a wave of depolarization and repolarization. It's not an electric current. It's just a series of voltage-gated ions channels opened and closed. Thank you for watching. Make sure you subscribe, and hopefully I made it wicked easy to understand.
In the last module, we took first steps towards understanding the electrical properties of individual neurons. We learned how electrical forces and diffusion give rise to membrane potentials, and we learned how cells can generate and propagate signals called action potentials, or spikes, along the membrane. Understanding the properties of the neuronal membrane is essential, but understanding just these properties isn't sufficient to give us insight into collective behavior of the billions of connected neurons in our brains. Luckily for us, we can approach neuroscience at many different scales and levels of analysis, and we don't have to confront the full complexity of everything all at once. That's what we'll be exploring throughout the rest of this course as we slowly go from our understanding of single molecules, such as ion channels, to the electrical behavior of neurons, to their collective behavior in small circuits, and finally onto how they become organized in large functional regions of the brain. Let's start simple, though. Since we've examined one neuron, a logical next question is, how do two neurons connect with one another? We'll first examine some basic cellular anatomy of neurons. So far, we haven't made too much of the fact that the majority of neurons are polarized cells. That is, they have one portion of the cell for receiving inputs and another portion for sending outputs. The parts of the cells that are specialized for receiving inputs from other cells are called dendrites. The word dendrite comes from the Greek word dendron, meaning tree, and as you can see, the dendrites have a branching, tree-like structure. A signal received by a dendrite is passed to the cell body. If there is sufficient depolarization of the cell body membrane to initiate an action potential, then an action potential is sent down the axon. The axon then carries the propagating action potential to another neuron. So what actually happens at the boundary between two neurons, between the axon of one neuron and the dendrite of another? This interface is called a synapse. There are two general types of synapses: electrical synapses and chemical synapses. Electrical synapses are less common in our own nervous systems, but they're simpler to think about, so let's start with them. Electrical synapses are basically pores between two cells that allow ions to pass through. They allow the passage of the electrical signal through to a neighboring cell without much fuss. It's not so different than just combining two cells into one larger cell. There are lots of reasons that nature might need synapses like this from time to time. They're fast and they allow cells to couple together with a high degree of synchronicity. But most neurons are connected together by a much more complicated structure called a chemical synapse. In a chemical synapse, rather than simply passing along an electrical signal from one cell to another, the action potential travels to the end of the axon and causes a chemical to be released into a very small space between the two neurons called the synaptic cleft. This chemical is taken up by the downstream neuron on the other side of the cleft. This chemical signal can cause the downstream neuron to depolarize its membrane, converting the chemical signal back into an electrical one. Or it can have other effects on the cell. This chemical step is slower than transmission across an electrical synapse, but it opens up an enormously diverse repertoire of different and more complex kinds of signaling. And synaptic function plays a critical role in computations performed by neurons. We'll spend the rest of this unit exploring the inner workings of chemical synapses, on our way to beginning to look at how networks of interconnected neurons give rise to behavior. We'll also look at the role of defective synaptic physiology in neurological and psychiatric disorders, and we'll see how synapses can be targeted by various psychoactive drugs and poisons. Finally, we'll wrap up by looking at how synapses can change over time in response to external stimuli, playing a foundational role in how we learn and remember.